First, we're entering a single page. How we handle the layout is actually quite simple. Each page is composed of a header and data. It follows a header data structure. For data layout, a common method is to track how many tuples are stored in a page. Every time an update occurs, each time a new tuple is stored, it is actually appended to the end. If a tuple is deleted, or if there are variable length attributes within the tuple, the entire page layout becomes invalid. Therefore, the header needs to contain metadata to keep track of things like the overall page size, whether the page is 4 kilobytes or 8 kilobytes. For example, it includes a checksum for verification and also its version, visibility and compression information of transactions, and self-content information. All these pieces of information are included in the metadata. The metadata organize this information accordingly. When setting up the data and configuring the tuples, there are two different layout methods. One is a slot page method, and the other is the log structure method. This method helps address issues such as when a tuple is deleted or has variable length attribute, and gaps appear between tuples. This approach avoids the fragmentation issue, where, for instance, when I delete a tuple, the first slot is occupied, the second is empty, the third is empty, and the fourth is occupied again, resulting in significant fragmentation. So first, let's look at the slot page method. What is the slot page method? It's a slot array. This slot array maps the starting offset of tuples. The header record, it first has a header. In this header, it records the number of slots, the starting position of the last used slot, and a slot array that tracks the starting position of each slot. The slot array maps the starting offset of tuples. After mapping, what does it look like? The first slot array element, 0, maps to tuple 1. The second slot array element, 1, maps to tuple 2. When inserting a tuple, the tuple is inserted at the end of the page layout. The slot array is arranged from front to back, 0, 1, 2, 3. The tuples 0, 1, 2, 3, 4 are inserted towards the end. When the slot array continues to insert 3, 4, 5, 6, the tuples keep getting inserted. When they meet, it indicates that the slot page is full. The entire page has been occupied. So it's a very good method for managing. When deleting, I just need to remove the slot array and the tuple. Then I can continue inserting until the header and the slot array and the number of tuples indicate that the page is full. This means that the page is fully occupied and the slot page is fully used. This is one method of page layout. However, today we are not focusing on the slot page method. Instead, we are talking about the log system. How is the log system implemented? How is the log system generated? It actually has a very good and a long history. Around the early 1990s, people started to set this up. In the early 1990s, there was a relevant historical context. In the last session, I gave you an overview of the development of databases from the 1980s, and then into the 1990s and 2000. In the early 1990s, the performance of computer hardware began to grow explosively. The CPU speed became faster and faster. As you know, with the 486, 586 Penta, the CPU speed kept increasing according to Moore's law. Memory also became larger and larger. Although the sequential read speed of hard drive, as we discussed last time, for example, solid-state disks, and their read-write speed increased, the random read and write speed was still limited by physical seek time in mechanical hard drives and by garbage collection in solid-state drives. Thus, the time was significantly constrained. On the other hand, at that time, file systems like the Unix file system and FFS had a lot of random read and write operations. So the performance of random read-write, including reading from and writing to the hard drive, became a performance bottleneck for the entire system. Due to the presence of the page cache, early researchers of log file systems believed that random reads were not a major issue. With an increasingly larger memory, most operations could be cached. Therefore, the log file system aimed to reduce random writes to the hard drive, converting random writes into sequential writes. How do we reduce random writes? They use a very simple idea. They treated the entire disk as an append-only structure. It only appends data, continually adding to the end. This append-only log is always written sequentially. When we write new files, we append them sequentially at the end of the file. The log structure file system does not modify the original content. It appends the changes to the end of the disk. It only stores log records, not tuples in pages. For example, when we record log entries, we log database modifications. When I add a tuple to the storage, I record this insert in the log, such as ID equals to 1 and the value equals to 8. If I add another tuple or delete a tuple, I mark the tuple as deleted in the log. Similarly, for updates, I only include the modified attributes and the corresponding changes. Our CnosDB also uses log structure method. Essentially, it is a log file system. Logging helps address the issue of random writes by aggregating records in memory and sequentially writing them to the disk. The disk then stores incremental records. All data deletions and modifications are done through appending. This means that this records record modifications in an append-only manner, just like how we handle redo logs in databases. When using redo logs, we first record the log entries in the system, and then perform the actual commit log work. If the system fails, we can replay the redo logs to restore the system. This append-only approach to logging is a key idea in disk operations.